Hello everyone. In this video, we are going to predict the Indian air quality with the help of machine learning models. And in order to predict the Indian air quality, we will be working with a dataset with columns including the types of pollutants present in the air, including sulfur dioxide, nitrogen dioxide, and other such chemicals. And in order to predict this Indian air quality, we are going to take the help of both machine learning models, which are the classification models as well as the regression models. And in order to work with this data set, we'll have to first import a few libraries. And as you can see over here, we have imported a few libraries. And the first import over here is the pandas. So pandas is a Python library which will help us to create data structures. And not only creating data structures, pandas will also help us to manipulate those data structures. So we are going to read our data set with the help of pandas again. We will read it as pd.read_csv, and that is done with the help of pandas again. And the second input over here is NumPy. So NumPy stands for numerical Python, and NumPy is a Python library which will help us to work with arrays. And not only arrays, Python also has domain over algebra and matrices. And the next import over here is Seaborn. So Seaborn is a visualization library which will help us to visualize statistical graphs. And this is again based on Matplotlib. So when it comes to Matplotlib, as you can see here, our fourth import over here is Matplotlib. And what Matplotlib does is that Matplotlib will help us to create plots, and that's what Matplotlib does. And then over here, as you can see, we have imported warnings, and we have used warnings.filter warnings. What this import does is that whenever we run a machine learning model, so sometimes we are indicated with some warnings, and this import will remove such warnings and directly run the machine learning model, and it will basically filter all such warnings and ignore all those warnings. And then the other import over here is the label encoder. So we have imported label encoder from sklearn.preprocessing. So what it does is that, let's say we have a data frame which has column which is categorical in nature. So when it comes to categorical variables, they are nothing but variables which are object type. Or let's say let's take an example over here. Let's say we have a column called as color. So the color column is going to have red, blue, green. So such columns are called as categorical. And what label encoder does is that it will convert all the categorical columns into numeric ones. And then we have imported a train test split from sklearn.model_selection. So what this does is that it will help us to split our data into training and testing parts, and which can be used to run machine learning models and compare the actual values and predicted values. So this is what train test split does. And after that, we have imported machine learning models. Like we have imported linear regression, and then we have imported decision tree regressor, and then we have imported a random forest regressor. So these are all the machine learning models that we are going to use in order to find out how our machine learning performs. And these models can be again compared based on performance. So not every model is going to work in a similar way, and every model is going to give us different results. And in order to compare how each model has performed, we will use the help of metrics. So these are nothing but evaluation metrics. So evaluation metrics will help us to see how a specific model has performed. When it comes to linear regression is a supervised machine learning algorithm where the predicted output is continuous in nature and has a constant slope. And then we have our decision tree regressor. So decision tree regressor uh, or decision tree classifier. So basically decision trees are used for both regression and classification problems. So we are going to begin working with decision tree regressor. So what a decision tree will do is that it breaks down a data set into smaller and smaller subsets, while at the same time an associated decision tree is incrementally developed. So this is our second model. And then we have a random forest regressor again. So a random forest is a meta estimator that fits a number of classifying decision trees on various subsamples of the dataset and uses averaging to improve the predictive accuracy and control overfitting. So what it really does is that when we use decision tree regressor, we are always going to see an overfit, and that overfitting problem will be overcome with the random forest regressor. So a random forest regressor is less likely to show us an overfit as compared to decision tree. And over here you can see I have imported metrics. So these metrics are going to help us evaluate our models and check how our model has performed. And we can again use other models as well, which is the XGBoost regressor and so on. But for now, let us see how these three models have performed. And again, I've already told you we are going to also use classification models on this data set. And those classification models are not going to get evaluated with the help of mean absolute error, mean squared error. These are for the regression models. And over here, these accuracy score and confusion matrix are for the classification machine learning models. So let us see ahead. And as you can see over here, this is the pd.read underscore CSV. So this code will read the dataset, and the dataset is in the form of a CSV file. And that's why we have used this pd.read underscore CSV. And then we have used this encoding is equal to Unicode escape. So if we do not use this encoding, then we are going to have a we are going to have a different data set, like the column names are going to miss, and the data set is not going to look uniform. So we have used this encoding is equal to Unicode underscore escape, and this is the resulting data set over here. And we have used df.head, and this is how our data set looks like. And in order to see, or we have to understand this data, so let us see what this data is all about. So let us go ahead and see the shape of the data set. And when we use df.shape, what it really does is that df.shape will display the total number of rows and total number of columns present in this data set. And as you can see over here, we have 4,35,742 rows and 13 columns in our data set. And you can see we have STN code and sampling date, state, location, agency, type, and these are the pollutants. These are the chemical names of the pollutants, and we have the date over here. And let us go ahead, and as you can see, I've used df.info. So what df.info does is that it will give us a overall information of the data set. Like as you can see over here, we have the column names. The column names are going to be displayed under the column called column. And then over here you can see the non-null count. So what this thing shows us is that, as you can see over here, the total number of rows in our particular data set now is 4,35,742. So wherever there is a mismatch in these numbers and these numbers, it means that there are null values present in that particular column name. So over here, we have only 291,665 rows over here. That means that there is a mismatch in this particular column, and it means that there are null values present in this particular station code column name. Same thing again, we can see over here that out of 4,35,742 rows, there are only 4,35,739 rows present in our sampling date column name. So that means that there are three missing values in this particular column called sampling date. Okay. And same thing again follows with the other column names as well, which is the state column. And among these columns, there is one column called as PM2 underscore 5. And as you can see, among 4,35,742 rows in our data set, there are only 9,314 columns available in this particular column name. That means the remaining columns are missing, which is more than 80% of the data is missing in this particular column called PM2 underscore 5. And apart from showing the null values present in the data set, the other thing that df.info shows us is the data types of that particular data set. So let's say we have a column station code. It shows us that this station code is of object type, and wherever we have the numeric column names like the SO2, NO2, you can see over here they are of float types. So it's nothing but decimal values. And as let us go ahead and see, SO2 and NO2 are of float types or decimal values. So apart from showing the presence of null values, df.info will show us the data types of that particular data set. All right. And the next code that we have used over here is df.isnull.sum. So what this does is that it will give us a clear picture of the total number of missing values present in that data set. So as we saw earlier, I told you that in this particular column sampling date there are only three missing values or null values, and it will show the total number of missing values. As you can see, the sampling date has three missing values. The station code has 1,44,077 missing values, and so on. And as we saw earlier, that PM2 underscore 5 has a lot of missing values present in this particular column. And so this is what df.isnull.sum shows. It gives us a clear picture of all the missing values present in the data set. And then over here, the next code over here is the describe. So we use the describe functions on the data set, which is the df. And what the describe function will show us is that it will display us all the descriptive statistics of our data set, and it will work for only the numerical ones. And wherever we have a numeric column, uh, only those descriptive statistics are shown to us using using the describe function. And we can see over here the minimum value present in this column SO2 is 0, and the maximum value present in this particular column is 909, and the same for other columns as well. The minimum value present in the NO2 column is 0, and the maximum value present in this particular column is 876, and so on. So the other descriptive statistics also include mean, standard deviation, and again we saw the minimum and maximum values over here. So this is what the df.describe function shows us. It will also help us to check if there are any outliers present in the particular data set or not. And the next function we have used over here is the nUnique function. So the this code over here will display all the unique values present in our data frame. And as you can see, the station code has 803 unique values, and these are the sampling dates. There are 5,485 unique values in this column. So it will display us all the unique values. And over here, in order to understand the column names, as you can see, we have column names in code. So what we have done is we have used the df.columns. So this will display us all the column names present in our data set. And as you can see over here, this is the description of this particular column names. So STN over here stands for station code. Sampling date stands for date of sample collection. And then we have state, which is the name of the state of our country. And then we have location, the location where the sample was collected, or the sample collection location. Then we have the agency type over here, which is the type of area. And then we have SO2, which stands for sulfur dioxide concentration. And these are all the pollutant names present in the environment. This is the NO2 or nitrogen dioxide concentration. And RSPM over here stands for a respirable suspended particulate matter concentration. And then we have SPM, which stands for suspended particulate matter. And then we have location monitoring, and PM2_5 stands for particulate matter 2.5. Then we have the date column in the end. So now we have understood the basic types of we have the basic information on this data set. Like we saw the presence of null values, and we saw the minimum and maximum values. We saw the descriptive statistics and types of data present in this particular data set. And now let us go ahead and visualize our data in order to get a more clear understanding. And the first visualization that we have done over here is the pair plot visualization. So what this pair plot visualization shows us is that it shows us the scatter plots, and wherever we see the x-axis over here. So in this particular scatter plot, SO2 is on the x-axis and PM2_5 is on the y. But when it comes to the second scatter plot over here, the x-axis has been changed, whereas the y-axis remains the same for this for all these scatter plots over here. So only the x-axis will change over here. That is, NO2 is on the x-axis now, but PM2_5 is again similar. And in this scatter plot, we have RSPM, and again the x-axis has been changed, whereas the y-axis remains the same. So these are all the scatter plots as we can see in our data. And the next visualization, what we have done over here is we have used value_counts to see all the states present in this particular column called as state. And as you can see, the state Maharashtra has the highest count with 60,384 counts, and followed by Uttar Pradesh, and the minimum counts are for Lakshadweep and Andaman Nicobar Islands over here. And we have used this visualization over here, and we have used histogram, and we have used the state names on the x-axis and frequency of their occurrence on the y-axis over here. And as you can see over here, so this is how our histogram looks like when we take state on the x-axis and their frequencies on the y. And the next visualization over here is of the type, whether the type column, let's see what are present in the type column. So as you can see over here, this is the area, this is the type of area, whether if it is residential, rural or industrial area, and such other areas over here. And we have done a histogram. Again, we used a histogram to plot this column called as type. And then we can see that the counts of residential rural areas is higher compared to other areas. The same thing can again be done with the help of value_counts. And as you see, this is the count, this is the total number of count, which is 1,79,014. And let us go ahead with the other visualization. Now we have taken the type of agency on the x-axis. It basically shows us the type of agency or which state of the agency it belongs to. So here we have Maharashtra State Pollution Control Board and such other agencies. We have taken the agencies on x-axis, and we have used the histogram again, and we can see now the occurrences of these agencies, and these are all the agency names. The other visualization over here is our bar plot. So what we have done over here is that we have taken the name of the state on x-axis, and we have taken the sulfur dioxide on the y. So as you can see, this will show us which state has the higher level of sulfur dioxide present in their environment. So over here we can see that Uttaranchal, Uttarakhand and Jharkhand. So these states have uh, a higher SO2 pollutant in their environment, and the least amount of SO2 pollutant is found in Nagaland, Mizoram, and then we have Chandigarh as well. So this will show us the total pollutant level, which is the SO2, and it will show us which state has the higher SO2 levels in their particular environment. And we have used another plot over here. We have used plot.bar. So this will basically show us the correct picture. It will give us a clear picture like which state has the lowest and which state has the highest SO2 pollutant in their environment. So the difference between this code and this code is that we have sorted values, and we have used the group by function over here. So basically these both codes are similar. The only difference is the way they have been plotted. So we have plotted the this uh, plot in the ascending order, and as you can see, this plot gives us a clear picture as compared to the previous plot, previous bar plot. And then we have used another plot. Before we compared the SO2 levels, now we are comparing the nitrogen dioxide level. And as you can see over here, West Bengal has a higher NO2 level as compared to other states. And after West Bengal, we can see that Delhi has again a higher NO2 level, and the least amount of NO2 pollutant is found in states like Arunachal Pradesh, and then we have Mizoram as well. So again, we will plot this in an ascending order, and this is how the plot looks like once it has been arranged in an ascending order. And as you can see over here, Arunachal Pradesh has the less amount of NO2 level, and West Bengal has the highest, followed by Delhi, and then we have Jharkhand at the third place, and followed by Bihar. So this is a better plot compared to previous, as it gives us a clear picture. And over here again we have used the state on the x-axis, and here we have given the RSPM on y-axis over here. And over here we can see Delhi again has the highest RSPM level, and the least amount of RSPM can be found in Sikkim. So we have used the state on x-axis y again, but now instead of the RSPM we have taken the SPM levels. And again Delhi has a higher SPM level, and the least is in Goa so far. So the better plot would be to use these kinds of plots which have been arranged in ascending order. And the other visualization over here is that we have taken PM25 on the x-axis, and sorry, we have taken the PM25 on the y-axis and state on the x-axis. So in this particular column, as we saw earlier, that more than 80 to 90% of the data was missing, and this is the missing areas where we don't have any data. And so far Delhi again has the higher PM25 levels. Anyways, let's go ahead and now, in order to use machine learning models, we have to basically impute the missing values, as missing values are not a good way to run the model. So basically we'll have to first treat these missing values and then run the machine learning models. So again, we have used the same technique over here, but now we are going to calculate the percentage of missing values in order to decide if we have to keep that particular column or drop that particular column. And in order to do that, what we have done is that we have used the df.isnal.sum again, and we have sorted all the values in a descending order. So as you can see over here, these are all the null values arranged in a descending order. And as we saw earlier, PM2 underscore 5 has the highest amount of missing values present in that column, followed by SPM, which has 2,37,387 missing columns, and so on. And as you can see over here, it is only the state column which does not have any missing value present in the data set. So now we are going to calculate the percentage of missing values. And in order to calculate the percentage of missing values, we have used this code over here, which is called as the null values percentage. And we have calculated the percentage over here. And what this code says us is that it takes the sum which is the df.original.sum, and divides it by the df.original.count. So over here, count is nothing but it will return the non-null value, and then we multiply it by 100, and then we sort the values in descending order, and we store all these values in null values percentage. And then over here, what we do is we concatenate the null values and null value percentage, and over here we have given the axis equal to 1, and this is the total. So total will show us the total missing values, and percent will display as the percentage of those missing values over here. So we have concatenated the total null values and their percentage of missing values for further imputation or column deletion. So using this, we can check the amount of missing values as well as the percentage of those missing values, and later we can decide if we want to keep that column name or drop the entire column name, or looking at the percentage, we can also decide if we want to impute that particular column name. And over here, we have displayed the missing data with percentage. So over here, there are in this column called PM2 underscore 5, there are around 4,26,428 missing values, which account to around 98% of the missing values in the entire data set. So in this particular data set, this column PM2 underscore 5 has 98% missing values in that particular column name. So whenever we have more than 60% or more than 50 to 60% of the data which is missing, then we usually drop that entire column. And even though we impute it, it's not a good idea. So basically, whenever you have more than 50 to 60% of missing values, then you can go ahead and drop that entire column. And then over here, we have SPM column. So over here again, we have around 54 to 55% of the missing values. So again, a lot of missing values are present in this particular column SPM. And then we have agency again, which has around 34% missing columns. And then we have station code, which have 33% missing columns in them. But whereas when you come to state, you see that there is zero missing value, and the percentage over here is very low. That means basically there are no null values in this particular column. And then over here we have these columns NO2, type, SO2. So basically these column names have very few missing values in them. So we can impute them. So currently, as they are important numbers, we are not going to impute them. Rather, wherever we have null values, we will replace them with 0. And so whenever you impute data, first we must check the type of the data that we are imputing. So whenever we are imputing categorical data, we basically impute them with the help of mode. And whenever we impute numeric data, we impute them with the help of mean. So over here, again, there are a few column names in our data set which are pretty much of no use. So we have dropped those columns, like we have the agency. So this particular column name is of no use for us for now. And we have dropped that particular column, as well as we have dropped the station code. Again, we have no use of this particular column. Then we have dropped the date. We have dropped the sampling date, as well as we have dropped the location monitoring station. And we have used in place equal to true. That means it will drop the entire column now. And now if we check our total is null.sum, we can see that these are all the remaining null values in our columns. And after dropping the column names, this is how our resulting data set looks like. Now it has a column called state, location, type, then SO2, NO2, RSPM, SPM, PM2 underscore 5. So what we have done over here is, as I told earlier, wherever we have categorical data, we impute those categorical data with the help of mode. All right. And over here we have used that particular column, which is the location, and we have filled the null values with that particular column's mode. And again, we have another column over here, which is type. Again, even this column had some missing values in them, as you can see over here. So we have again imputed this categorical column with the help of mode. We have basically filled that particular column with that particular column's mode. So over we have used the df underscore type, and fill the null values with the df underscore types mode. And wherever we had null values, what we have done is, instead of imputing these numbers with the help of mean or with the help of mean, we have directly filled those null values with 0. And we have used this function over here. We have df.fill na, and we have filled the null values with the 0 value over here. And after we have done our imputation over here, we have again checked the total number of null values with the help of df.isNull.sum. And as you can see, we have successfully imputed our null values over here. And then this is the resulting dataset after the imputation. And in this particular dataset, there are no null values, and wherever we had a null value, we have replaced those null values or NA values with the help of 0. And wherever we had the categorical data, we imputed it with the help of mode. And the next important thing that we have to use over here is that we have to calculate the air quality index. And in order to calculate the air quality index, we are supposed to use a function, and we have used a formula over here which can be found on the internet. And this formula is used in order to calculate the air quality index for SO2. And this SO2 has been calculated with the help of a formula over here. And you can again Google this on the internet. You will find the formula to calculate the air quality index. And based on the sulfur dioxide levels, we have calculated the individual pollutant index of this SO2, and we have called it as SI over here. And what we have done over here is that we have created a function, and in that function we have given a range, and using the uh, if and if else loop, we have assigned a formula over here. Again, this formula can be found on the internet, and this will basically calculate the SI. And what we have done next is that we have created a data frame which has the original SO2 values and the SOI, which is nothing but the individual pollutant index. And we have created this index values. And then after calculating, you can see that this is our calculated values from the SO2 or the sulfur dioxide column. And this value, the SOI, and other values like the NOI or the index for the nitrogen dioxide will be used in order to calculate our final column, which is the air index. And so for now, we have created a function where we have given this formula, and this will calculate the SOI values or the pollutant index for sulfur dioxide. After we do that, we repeat the same process for other columns. Example, nitrogen dioxide. Again, there is a formula to calculate the individual pollutant index. And using this function, again, we have given a range and then use the formula in order to calculate the individual pollutant index for the nitrogen dioxide gas. And the same process has been repeated again for the other remaining columns. And as you can see over, this is the original NO2 values. And from that, giving a range, we have created a function which calculated the pollutant index. And then same process has been repeated for this column, which is the RSPM. And again, these codes can be, these formulas can be found on the internet in order to calculate the individual pollutant index. And again, we have specified a function over here. We have defined a function and we have given a range. And from that range, we have calculated the RPI or the individual pollutant index for the RSPM, which is called as respirable suspended particulate matter concentration. And again, this column will be used for calculating the air quality index. And over here, there are a lot of null values that had been present in this particular column. So you can see that there are a lot of 0 values over here. But when we check for the SPI column again, you can see that again we had a lot of null values in this particular column, which we replaced with the zero value. And again, that's the reason why we can see a few zeros over here. And again, this is the defined function for calculating the individual pollutant index for SPM, or the suspended particulate matter. And again, we had given a range, and using that we used a formula in order to calculate the SPMI, or the individual pollutant index for SPM. And because there were null values, you can see that there are a lot of zeros present in that particular column. And now, after we have calculated these columns, which is the SPI, RPI, and NOI and SOI, after we calculated all these pollutants, individual pollutant index, what we have done is that we have calculated the air quality index. And again, this formula had been googled, so you can check the formulas for calculating the air quality index from the particular gases that we saw above. And using this formula, in the end, we have created a data frame which has these following columns. And using the lambda function, we have calculated the AQI, which is the air quality index column. And then, as you can see, this is our resulting data set now. We have used the data.head, and we have the state column, and then these are the index that we calculated. And using this index, and we specified this formula, finally calculating the AQI, or the air quality index. And these are all the air quality index. And what we have done next is that we have used a loop, and we have specified wherever the value is between 50, which is greater than 50 and less than 100, we have given a label called as moderate for that particular values. And wherever we have values which are less than equal to 50, we have labeled it as good. And wherever values are greater than 100 or less than 200, so we have assigned that particular label as poor. And values between 200 and 300 are specified or labeled as unhealthy. And values between 300 and 400 are labeled as very unhealthy. And values which are greater than 400 are assigned as hazardous. And this is the air quality index. So we basically have used these values, which is the AQI, and we have given we have defined a range, where we have given a range between these particular values and labeled them as moderate, poor, unhealthy, very unhealthy, and hazardous. And then uh, this is our final data set over here, which is ready for machine learning. Now we can go ahead and apply our machine learning models. So as you can see over here, we can apply two types of machine learning models in this particular data set, where one is the linear regression. And when we use the linear regression or any regression models, at that point of time, all these columns become the independent columns, and this AQI over here becomes the target column when it comes to regression use case. But when it comes to classification, we can use all these columns again, which are independent in nature. But for classification, our target column will become the AQI range over here. As you can see, there are labels over here, and whenever we predict labels, we do that with the help of classification algorithms. And whenever we predict a number, we do it with the help of regression models. And as you can see over here, we have used the AQI range dot value underscore counts to see the overall counts of the elements present in that particular column. So good repeats for 2,19,643 times. So this is the count of this good present in that particular column. And the least amount of variables present is the very unhealthy. So this will show us the total number of elements and how many times these particular elements repeat in that particular column. So we can see that a lot of counts are based on this particular column name called good. And then what we have done over here is, in order to apply machine learning, first we have to divide our data into independent and dependent columns. So the other way is we can directly use these column names, and we have taken the SOI, all these index values of these particular pollutants, and we have assigned them as our independent columns over here. And these are our X values or X column names. And then as we are predicting a number, we have taken the AQI or air quality index on the Y. And as you can see, this is our X dot head. So these are all the X values. And then over here, these are our target columns. So these are basically our independent columns. And these are all our dependent columns. And after that, after we have split our data into independent and dependent columns, the next thing that we have done is that we have separated our data into train and test, and we use the train test split function over here. And we had imported this previously from model underscore selection. And over here, as you can see, we have taken our independent and dependent column names over here, which are the X and Y. And the next thing that you can see over here is that we have specified a test size, which is 0.2. So what the 0.2 over here says is that around 80% of the data will be used for training purpose, and around 20% of the remaining data is going to get used for test purpose over here. So if we change the value from 0.2 to 0.3, then our training size will become 70% and our test size will become 30%, and 30% of the data will be used for testing purpose and 70 will be used for training purpose over here. So this is what this test size tells over here. And then we have given a random state. So what random state will do is that, let's say among 5 people, 2 people use the same random state. Here in our case it is 70, then those 2 people are going to get the similar results. And over here what we have done next is that we have printed the X train shape, X test shape, Y train shape and Y test shape over here. And over here these are all our shapes of X train, X test and Y train, Y test. And then we have used our machine learning models. So over here we have used linear regression, and after that we have used a decision tree regressor, and then we have used a random forest regressor in the end. And these are all our regression models which we are going to use in order to check, in order to perform machine learning. And as you can see over here, when we use linear regression, what we have done over here is that we have used model is equal to linear regression. And over here, when we fit our model on X-train and Y-train, we can see the model has been fit on the linear on the X-train and Y-train. So linear regression is a supervised machine learning algorithm where our predicted output is continuous in nature, and it has a constant slope. So this is what our linear regression model is all about. And then what we have done is we have predicted the model on X-train, and then we have predicted the model on X-test. And in order to evaluate this model, we have used evaluation metrics like the root mean squared error, and then we have used the R squared. So the root mean squared error is supposed to be low in order to uh, check if our model is performing well. There are 2 things that we have to keep in mind. One is the root mean squared error, which is supposed to be as low as it can. And then we have the R squared value. So the R squared value, the better is when when the R squared value is closer to 100, the model is better, and the RMSE value when it is low as it can be. So the RMSE value, if it is close to 0, it's a good model, but the R squared value must be higher and close to 100. And then over here you can see that the RMSE value over here on train is 13, as well as on the test is same. And as you can see over here, the R squared value is high, which is 98% on train and test. That means it is a good model. But let us go ahead and check the other 2 regressor models, which is our decision tree regressor and the random forest regressor. And this is our decision tree regressor. Again, the same thing has been followed over here. We have used the decision tree regressor, and we have fit the model on X train and Y train over here. So what decision tree will do is that it will create a model in a form of tree structure, and it will break down a data set into smaller and smaller subset. And then the next thing is that we have predicted this decision tree on X train, and then we have predicted the decision tree on X test. And in the end, we have tried to calculate or evaluate our model's performance with the help of the same evaluation metrics, which are the root mean squared error and the R squared value. And over here, you can see that the RMSE is a bit high, and the R squared value is again 100 in both training and testing set. That means that the decision tree model is overfitting, and which is not a ideal model for predicting. So what we have done is we have used another final model over here for regressor use case, which is our random forest regressor. And over here you can see that we have used this random forest regressor and we fit this model on X train and Y train. So when it comes to random forest regressor, it is a meta estimator that fits a number of classifying decision trees on various subsamples of the data set and uses averaging. So using this averaging, it will improve the predictive accuracy, and unlike decision tree, it will not overfit. And random forest algorithm, again, it can be used for both classification as well as regressor or regression problems. So over here we can see that we have evaluated this model again with the help of root mean squared error and the R squared value. And over here we can see that the R squared value is again 99% on both train and test, and the RMSE train and test values, as we can see over here again, compared to linear regression model. I think the linear regression model has performed well compared to the decision tree regressor and the random forest regressor. And we have predicted the numeric values using the regression algorithm. But when it comes to the other columns like the AQI range, we cannot use this regression model over here. So what we have done is, to predict this AQI range, we have used classification models. And when it comes to classification models, we have used logistic regression, and we have used decision tree classifier over here. And then we have used the random forest classifier and k nearest neighbors classifier over here. So as I told earlier, random forest and decision tree are used for both regression as well as classification problems. So what we have done over here is that we have imported all these models, and over here, the other new algorithm that we have used over here, apart from decision tree classifier and random forest classifier, which we already spoke about, we have used the logistic regression and the k nearest neighbors or k neighbors classifier over here. So we already spoke about the decision tree classifier and random forest classifier. The other models which we use for classification now is the logistic regression, which is used to find out or predict the labels apart from the linear regression, which predicts a number. This logistic regression will be used to classify a particular label. And then the other model over here is the k nearest neighbors. So the KNN algorithm is one of the simplest classification algorithm, and it is the one of the most used learning algorithms. And when it comes to k nearest neighbors, it is called as a lazy learning algorithm, and KNN is a non-parametric model over here. And let us go ahead and apply these models for classifying. Our target column over here is now the AQI range over here. As previously we were predicting a number, we use the AQI as the target column. As you can see over here, the AQI over here contains numbers. So we use the regression algorithm. But over here now, we have used AQI range as our target column, and the remaining independent columns include the index values of the particular pollutant. And over here, this is our logistic regression model. And over here, we have missed this part, which is this splitting the data into train and test. So once we split our data into independent and dependent columns, we split our data into train and test. And over here, we had taken independent columns on x2, and these are all the independent columns. This is the x2, and our y2 had the target column or the dependent column, which is the AQI range. We have taken that over here. And here the test size is 0.33. As we talked earlier, these are the training and testing size. So around 77% of the data will be used for training purpose and 33% of the data will be used for testing purpose. And then again, the random state that we have assigned over here is 70. As I told earlier, if two people use the same random state, they are more likely to get the same results or similar results. And then this is the logistic regression model. So we have used the logistic regression, and then we have fitted this model on XTrain. And over here, we have mentioned it as XTrain 2, as we have already used XTrain and XTest when it came to the regression algorithms. In the classification, we have called it as XTrain 2, XTest 2, YTrain 2, and YTest 2. And over here, you can see that the logistic regression has been fit on XTrain 2 and YTrain 2. And then the model has been predicted on XTrain 2. And over here, we have given the print command. So this print command will display as the model accuracy on train. And then similar thing has been done, but it has been done on the XTest 2. We have fit the logistic regression on XTest 2, and then we have used the print command over here, which will display the model accuracy on test. And then apart from these two, we have used another evaluation metric over here, which is the kappa score. So kappa score will help us find out how well our model is performing. So kappa score is nothing but our evaluation metric, which will tell us how well our model has performed. And the next thing that we can see over here is after running this code, we saw that the accuracy on train is 72%, and the accuracy on test, the model accuracy on test is again 72% over here, and the kappa score is 58% over here, and this is not a very bad model. And the next thing that we have done over here is we have used this logistic regression model, and we have given individual values, and we have predicted the model on these values that we have manually given. So I selected values like 727. So whatever you see over here are nothing but the these values, the independent values: SOI, NOI, RPI, and SPMI. These are the index values of the pollutants, and that has been given over here manually. And then we have predicted the model, which is the logistic regression on these values. And as you can see over here, as we have used a classification model, we have been given a label over here. These are the values present in the target column. So the model says that these values are good, whereas these values are poor. And then we used the same model on these values. So 10 represents the sulfur dioxide index value. 2.8 over here represents the nitrogen dioxide index value, and so on. So these are the values, and the model predicts that these values are good. And over here, we have predicted on these values, and these values, the model has predicted this value as poor. So these are nothing but the target column or a dependent column called as the AQI range, which has been predicted by our model and apart from the logistic regression, we have used another three models, which is the decision tree classifier. And then we have used the decision tree, and we have fit this model on XTrain 2 and YTrain 2 again. And then we have predicted the decision tree on XTrain, and then we have printed this where it will print as the model accuracy on train. And then the same thing has been repeated, and we have used the decision tree classifier on XTest 2, and then we have printed the model's accuracy on test as well. Over here you can see this code This print statement, what it does is that it will create 50 dotted lines, as you can see over here. And then we have evaluated our model with the help of kappa score. And over here, as we are using a decision tree, the decision tree is more likely to overfit, and this can be seen over here. The model accuracy on train is 100, and then we have model accuracy on test, which is again 100, and then we have our kappa score is 99 or 100% again. So this shows us that the decision tree classifier is overfitting. And then let us go ahead with the random forest classifier. And over here you can see that the model has been fit on X-train 2 and Y-train 2. Again, same steps have been repeated. And then we have predicted our random forest on X-train 2. And then we have printed the model accuracy on train. And after that we have predicted the random forest model on X test. And then we have printed the model accuracy on test as well. And then we have printed 50 dotted lines. And then we have printed the kappa score, which is our evaluation metric. And as you can see over here, our model accuracy on train is 100%, and the model accuracy on test is again 100%, and the kappa score is again 100%. Again, this is a overfit. And in the end, this is our last classification algorithm, which is the k nearest neighbors, which is the non-parametric lazy learning algorithm. And over here you can see that the k nearest neighbors has been fit on X-train 2 and Y-train 2. Again, same procedure has been repeated, and these are our prediction on X-train, and this will print the model accuracy on train. And then we have predicted the model on X test, and then we have printed the model accuracy on test, and we have printed 50 dotted lines. And then we have used the kappa score. Again, this is an evaluation metric. Over here you can see that the model accuracy on train is 99, model accuracy on test is again 99, and kappa score over here is 99%. What we have done over here is that we have used this k nearest neighbors to predict on these values over here, and these predictions are correct. And after cross checking, we can say that the k nearest neighbors performed well. And when we pass these values, which are lower, we saw that these values has been predicted as poor by the k nearest neighbor model. And when we over here you can see that there are a few higher values over here, and that's the reason why this model has predicted these values as poor, poor AQI range or air quality index range. And then we have predicted the model, and intentionally the numbers have been given smaller over here, and smaller number means less pollutant index. And this model has predicted these values to be good. And then we gave higher values over here, which means the higher value, the higher the pollutant index. And as you can see over here, when we gave higher values, 325.7, 345, 798, 203, this model predicted that numbers as unhealthy, unhealthy air quality index. And whenever we gave low values, the model predicted those values to be good. And we have successfully performed machine learning models, both classification and regression, on this data set called as the Indian air quality dataset. And we have predicted the number using linear regression models, where we predicted the values. And using the classification model, we predicted the AQI range, and predicted if that particular values are good or bad or hazardous in nature. And that's it for this video, and hope you like this video. Until then, have a good day, and I will see you soon in the next video. Thanks for watching.